make sure that you do your homework and that at least for the first attempt, don't look at the solutions. Okay, don't look at the hints and try very hard. Also, you need a textbook. Okay, don't just rely on my slides. Use your textbook. The one I highly recommend is Johnson and Cutnell. It's very good if you want to review for biology. It connects a lot to biology, or if you want to take the MCAT. Another material that is very nice are these old, it's the old edition, not the new one, 2008 around there, SAT physics. Okay, it's like a summary of what we are doing. So it's college algebra. So it's a nice material. And also you have all those links in Canvas. Okay, talking about Canvas, so test number 1, it's gonna be on Tuesday. In person, on paper, multiple choices, except one question I forgot, but it's 20 questions. Okay, so if you have a DRC accommodation, it's your job to talk to them and to secure a spot for that day at that time, because I don't have extra time after this class. Okay, what else? You need to print out the equation sheet. You see, you have the equation sheet here. You cannot write down any notes on it. So if you think that something is missing, just memorize it. Okay, so get familiar with it. So make sure you print it out, bring it for the test. Okay, and so for example, here we have, we go down here. You see, you have all the equations here. Current is the rate at which the charges are flowing, or it's a coulomb per unit second. Resistance is proportional to the length of the connecting wire divided by the cross section. The power, the electrical power, is current divided by the voltage across. Delta means across. The current, this is Ohm's law. Okay, so it's proportional to the voltage, or it's the voltage across the resistance divided by the resistance itself. If you have a circuit in series, you add the individual resistances. And if it's in parallel, you have this magic equation or magic recipe. Okay? And what else we have here? There is a review of trigonometry down there. And here, so you know what a milli and a centi is. So it's your job to print it out, no note. You cannot write any note on it, okay? So make sure you get familiar with this equation sheet. Any questions? So, yeah.
You have a practice test for test one or no?
Okay, so for test 1, I'm thinking about it. So, I might do instead a video to review whatever you need to review. I have to do it. It's on my to-do list. So either a practice test or a video where I go over everything. Video might work best because not everyone do the practice test, but either you have to do it. I'm behind everything, so I will do it. So test 1 on Tuesday. Okay. So we were doing a parallel circuit. And so, for example, this one is easy because if you have, these are called branches. So you have one intersection here, one intersection there. So if you have 3 branches and they are all the same load, so you have the same load, okay, all you have to do 24 divided by 3. Otherwise, you do 24 to the minus 1 plus 24 to the minus 1 plus 24 to the minus 1, whatever. Okay, you add them up, and then to the minus 1, you get 3. No, no. 24 divided by 3? 8, right, 8, yes. So then the main current that you are draining from the battery will be 12 divided by 8. And then that current here will be divided in equally amount in each of these branches. Okay, so let's do something more challenging. Now you could have a mixed. So you see, if you look at this circuit, you follow. You always go from plus to minus. You follow along, nothing happening, nothing happening. Oh, intersection. Intersection means it's a parallel circuit. So this little piece here, this component is a parallel circuit because you have two branches. And then it combines again together, and then you have another resistor here and coming back to the power supply. So you have two components, one component here, another component here. This component is in series with this one, but those two are in parallel. Okay, so I want to make sure you understand that. So I did I'm prepared. Today I'm prepared. So you have a power supply, 120 volts. You have two loads. Those two loads are in parallel. Very good. Okay, because you see you have one intersection, two branches, and then it combine again. And then you have another one here, 50 ohms. So I'm going to close the switch. So let's find the current. So you see, that will be the current drain, okay, from the power supply, 1.6 amps. So the current flows here, flow. And then you have the same load on each branch. So what do you expect it's going to be? So it has the same appetite. If you have a larger resistance, that means the current will be smaller. Smaller resistance, the current will be larger. But here you have 1.6 and you have two pipes. So it's going to be
0.8.
very good, 0.8. What's your name? Cora. So it's going to be 0.8, 0.8. Makes sense? Right? You have 10 gallons and you have two pipes exactly the same size. So they're going to be divided in two. If you don't have the same resistance, so then it's another story, right? So if I increase the resistance here, of course, you're going to have less current here than you have there. It's not going to be equal because by increasing the resistance here, it's like you are squeezing the pipe. So you don't have that much water flowing here. You see the current is not going as fast. Is that clear? But I'm trying to simplify. So let's go back to my 50. So you have 0.8, 0.8 flowing through, 0.8 flowing through, up, intersection. The two branches come back in one. So how much we're going to have here? 1.6. Does it make sense? Imagine water flowing. So it's going to be 1.6, 1.6, 1.6, 1.6, 1.6, all over. All over. Okay?
Okay.
Yes.
So the load that's kind of by itself, would it be in series with the other two, or
Very good. It's going to be in series with the other two. So let's do that in our head. Ready? 50, you always start with the component that are in parallel, right? So 50 in 50 are in parallel. So what do we get? 50 and 50 are in parallel? No? Parallel. Parallel, that means the equivalent resistance is always smaller than the smallest one. So it has to be smaller than 50. So it's going to be 25 because you have two branches. So otherwise you do 50 to the minus 1 plus 50 to the minus 1 to the minus 1. It's going to be 25. So this one, okay, I can replace by a 25. And then it's being followed by, okay, it's a series. So it's followed by a 50. So 25 and then a 50, they follow each other. So it's the same pipe. Okay, they are connected on the same pipe. You have a 25 and a 50 on the same pipe. So what's going to be the equivalent resistance? 75. Okay, let's check if it is true. I'm going to disconnect here and I'm going to connect that here. And let's say, so this one doesn't count, okay? It's dead end, so it doesn't count. And I'm gonna increase to 75. Huh? Do you get the same thing? 1.6 up, 1.6, 1.6. So what matters is how much energy you are using from the power supply. Power supply is 120 volt. The current is 1.60. So the energy produced per unit second, the wattage is 120 times 1.6. So everything happens like you have a big load. This one, 75 ohms consume as much energy as the 50-50, and then what did he say? 20, was it 25 or 50? No, 20, 50, right? So that load here consume as much energy that if you cut everything here and you replace by one, which is 75. Is that clear? So let's go back. Okay. Oh, I'm lucky. Okay. So now we need to find the voltage drop. So let's do it and see where I am. So let's try to solve everything we can solve here. Okay, so this is 120 volt. This is what? 50 ohms. And then this is 50 ohms. And this is 50 ohms, right? So I can go step by step from here. Okay, I'm going to replace it by, and I will show you different way to do it, but 120. And then you have a 50 and a 50. They are in parallel, so everything happens like you have a
Yeah, with different lines.
so yeah, but what's the equivalent resistance here?
25.
25. And then here we have a 50. So with complex, you always start with the parallel, and then they follow each other. And then from there, so this is all mathematic trick to find how much current and even the voltage drop. Everything happens like you have a 75 ohms, right? So let's use Ohm's law now. The voltage drop, of course, is going to be 120. Okay, so what's the current flowing? It's going to be 120 divided by 75. It's going to be 1.6 amps. You see? And then you go back one step. Okay, you go from here to there, and then you go back one step back. So now you see that current here is flowing. Okay. So can I find the voltage drop across the 25 using Ohm's law? So you have 1.6 going through it. The resistance is 25. What's going to be the voltage drop? 40? Did you do 1.6 times 25? Okay. And then here you have 1.6 going through 50. You are leaving already? No? So it's going to be 50 times 1.6. How much is that? 80. And you could have guessed because 40 plus 80 is 120. It's called Kirchhoff law. Okay? Okay. So now I know. You go one more step back. Okay? So what do we know now? we know that's going to be 40 volt, and this is 80 volt. Do you agree? So, and the current here is 1.6, and we know that's going to be 0.8, but let's pretend we don't know. What's going to be the voltage drop here across this one? It's like a height. It's going to be between here and there. You are measuring the height, the voltage drop. It's going to be 40. Okay, they have the same intersections. So across here is going to be 40. Across there is going to be 40. So let's do 40 divided by 50. What do you get? 0.8. And that's going to be 0.8. You see how it works? And then 0.8, 0.8 is going to be 1.6, and it's going to be 1.6. Do you see how it works? Okay, so let's check here. I'm going to take a voltmeter. I'm going to measure the voltage here, and it says 80 volt, right? Did I get that? 80 volt. The voltage here, it should be 40. So the connecting wire, of course, inside you have a sneaky resistance too, but we neglect them, okay? So it should be about 40 here too. Okay, it's also 40 here because we neglect the voltage drop across the connecting wire. Even though I told you that the resistance of a connecting wire is proportional to the length, inversely proportional to the area. And it's also 40 volt here, and that's going to be 0.8 and 0.8. Okay? Now the other way to do it, okay, which sometimes is easier when it gets more complicated, it's to do it the engineering way. So easier, I think. So you start with 120 volt, okay? And you think of that as a height. Okay, so height is 120 volt. You go pom 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 pom. Oh, what's going on here? You have two pipes. So you make two pipes. In this one you have 50. In that pipe here you have 50. So it's going to be the same size. If you have a smaller resistance, that will be a larger pipe. And then what's happening? Boom, boom. Oh, they combine again. Okay. And then what's happening? Pom, pom, pom. Another load. 50. Ah, this is base. And then you go from here. Okay. So you decide which way you want to do it. Okay. So I'm going to just replace this by 1. So that one will be replaced by a 25. Okay. It's like you shift. And then this one I don't touch yet. That's going to be 50. And then you take another step. So it's the same thing, but a different approach. And you pick the one you like. So a big zigzag, a small zigzag, and another a small zigzag. That's going to be a big zigzag here of 75 ohm. Okay. So from there, you use Ohm's law. You see, from 120 to base, that's going to be 120. Okay, so you have water flowing here or charge flowing. That's going to be 120 divided by 75, which is 1.6 amps. Do you agree? And then one step back. Okay, that's going to be the same current here, 1.6 amps. You see? Are you with me? Because 1.6 is whatever is being produced by the top here. That's your pump. Okay, it's pushing water here. It's like a pump. And so the voltage drop here, okay, we can find the height, okay, because you are measuring height. The potential difference is a height. So 1.6 times 25, it's going to be 40 volt. And 50 times 1.6 is going to be 80. And then boom, one step back again. So this is 80. You see the same height. And now I know this is 40. Okay, and you have here the current here is 1.6, so it's the same 1.6. So it's like water coming from the top of the mountain. Chung chung chung, it's gonna rain here. I mean, it's going down slow. This is 1.6. Now, if you use Ohm's law, so 40 across divided by 50, that's going to be 0.8, and that's going to be 0.8. Okay? So either you use this way, okay, it's in your book, textbook. Oh, I like this one. Maybe this one is easier. Okay, any question? Okay, so apply that to this problem here. Alors, it depends on students, right? Some people they get it right away and you say, okay, I have two branch, boom, boom, and then I have another one here. Or you have to do a drawing. It really depends on you. So you do the way you like the most. The question is find the current drain by the battery, drain from the battery and find the current here or find the voltage here and find the voltage there. So you have it's up to you, okay? You have different way to do it. I don't know how you want to do it. I like to do the engineering way, but you don't have to. Six, 12, and 8. Okay, so I do it this way, but you can go faster, okay? You don't have to do it this way. Boom, boom, boom. Boom, boom, boom. So you have 6 to the minus 1 plus 12 to the minus 1 to the minus 1. What you get? Huh? Oh, very good. So small zigzag and a small zigzag. What's your name? Natalie. Jassy? Jackie. So 1.5 volt. Okay. So it's like a big, 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 big one of 12. 6 to the minus 1 plus 12 to the minus 1 to the minus 1. Like the recipe. And then here. So this one is in parallel. Yeah. So then it's going to be in series because look, there is no intersection. It's like a small zigzag and then another zigzag. So you add them up. It's one pipe. Whereas here it's two pipe. Okay, so imagine water like you have a mountain here and you have pipes going down slope. So I don't know if it's a good mountain or not, but you get the idea. So what's going to be the current? So you see here, the voltage drop is 1.5 volt. So the current flowing will be very good amps. Do you agree? Or 125 milliamps. So then you take one step back. So that means in all this pipe here, you have 0.125 amps because this is what is burnt out by your station at the top of the mountain. Okay, it's like your pump. It's pumping water and that's it's producing water, so it's 0.125 amps. So now we can stop here. We can stop a little bit and we can find here the voltage drop here. Okay, so you use Ohm's law. So remember, you are measuring height. So for this one, it's going to be 4 times 0.125, and you get 0.5, 0.5 volt, and this one is going to be 1. And we can check 1 plus 0.5, so it's the voltage drops. Boom. And then boom. And then nothing is left. Okay, and then you take one step back. Okay, so this is 1 volt, and this is 0.5. Okay, and so if you do that, now you can find the current in each branch. So now you still have that one, what is it, 0.125 amps. So in that here, water falling from the top of the mountain is 0.125, and here you have two branches. So you're gonna have a current I1 and a current I2. So this one has more resistance. That means that your pipe is tighter. So you expect less current. This one has a smaller resistance, so it's going to be twice as big, or the cross section will be twice as much because this is 6 and this is 12. Okay? So if you use that strategy, it's not that hard. So I1 will be equals to the voltage drop. So 0.5 times 6. I2 will be 0.5 times 12. I don't know what you get. 0.0833 repeating. 83333 repeating. So when you have repeating, you have to include everything when you add. Okay, because repeating that means it's a ratio. Okay, it's a fraction, and the other one is 66666 repeating. And when you add them up, if you keep all the decimal, you get 0.125 amps. Is that clear? Now, did I have to do that? No, you don't have to do that. It's up to you. It's how you see the things. What is true is that you need a textbook, okay? You need to go over. You have your textbook and a lot of links. Is that clear? Okay, so let's do one thing in our head. Find the equivalent resistance. So always start with the parallel. So you see you have, okay, boom, boom. You have two branches coming back and then three branches. So this one, what do you think the resistance is? 3 and 3 in parallel. 1.5, very good. Okay, and you remember when we did the computation in arithmetic, okay, you bring it down, that's going to be 3. And then you 3 and 3 and 3, that's going to be 1. And they are all in series. So that's going to be 5.5. So 1.5 plus 3, 4.5, 5.5 ohms. Okay. Okay, so here it's from your book. I'm pretty sure it's from Johnson and Cutnell Physics. And you see how they do it? So you have one here, and then you have two branches. But inside one branch, you have a zigzag and then another zigzag. So they combine them together in one single one, 470. Is that making sense? And then they're going to focus on those two here. So you have 180 and 470 in parallel. So it's going to be 180 to the minus 1 plus 470 to the minus 1 to the minus 1, right? So you replace that by 130. And then you have 110 and 130, so you have 240. So 240 will be the equivalent resistance. So that's how it's done in your book. So of course you can do that. You don't need my schematic. My schematic is useful when you are asked, for example, to find the current flow here or the current flow there or the power consumed by this one. So maybe the way I do it is easier. Okay? So let's do things in our head now. We always go inside as much as possible. So we're going to take care of this one. So you have two branches. And in this branch, you see they are in series because it's one zigzag and then one zigzag. So you can replace it by one big zigzag. But in that branch, you have two in parallel. So first we have to get rid of that. So 4 and 4 in parallel. How much is that? 2. Very good. And then I have a 2 and the 8. How much is that? 10. So I have 10 here. And 7 and 3 is 10. So I have a 10 and a 10 in parallel. So that's going to be 5. Very good. Okay. And then if you want to find how much current is drained, you do 60 divided by 5.
Well,
Thank you. 12 amps. So you have 12 amps. And you see the same thing here. Then so 12 amps. You're going to have 6 amps. And then here you have 6 amps. Do you agree? And then 6 amps divide in two branches. So you're going to have 3 and 3 combined together. Then 6. So 6 here, 6 here, back to 12. Isn't that cool? So this is a configuration. It's used in electronics. It's called R to R, R to R network. So you see here, the one and the one, are they what? In series or in parallel? This one. Series, you see, they are following each other. There is no branches, right? So 1 and 1, it's going to be 2. And then you have a 2 and 2 in parallel, that's going to be 1. Okay, let's try this one. 1 and 1 is 2. 2 and 2 is 1. And then I have 1 and 1 is 2. And 2 and 2 is 1. So regardless of this network, I'll always end up with 1. You see? 1 and 1 is 2. 2 and 2 in parallel is 1. 1 and 1 in series is 1 and 1 in series is 2. 2 and 2 in parallel is 1. And so forth and so on. You say, why would you do something like this? They use that in electronics to go from digital to analog, I think. So it's called R to R. It's wild. So this drawing comes from a book. So it's a conceptual book. It's called Conceptual Physics. It's by Paul Hewitt, who is very good at drawing. So this is a 6-volt battery, and you have a load here. What do you think the voltage is going to be? 6, very good. Okay, it's a voltage drop. Voltage is a property of 2 points, right? So these are the same loads. So this is 6 volt, and now the voltage across here is 3. So it's not happy. It's a circuit in series. So instead of getting the 6-volt drop, it's getting 3-volt drop. We suppose they are the same loads. in addition to that, the current will be divided by 2. So divide by 2 the current, because you multiply by 2 the resistance, and you divide by 2 the voltage for each one of them. So you divide by 4 the power. So not happy. What about the voltage drop here? Yes, you're right, 2. 2 volt, 2 volt, 2 volt. And the current will be divided by 3, because if you have R plus R plus R, that's going to be 3R. So 3 times the resistance, the current will be divided by 3. So here we have 2 branches in parallel. So R and 2R, R and R, that's going to give you 2R. So the voltage drop across each one will be, no. So across here, no. Look, it's connected to, how much do they get? 3 each. So that across here will be 6. Because you are taking a measuring tape and you move from here to there, that's going to be the same thing from here to there, right? So in parallel, all the branches in parallel have the same voltage drop. So from here to there, it's going to be 6. So across each one is going to be 3. If you have a hard time to digest, you take the seam and you play with it. And the voltage drop is 6. This one is very happy. Okay, these are not happy. They have to share the voltage, and the current is divided by 2. All these are what is it called? This parallel. Okay. When they draw it this way, it's just for textbook. Because for textbook, it's not easy to do something like that. But it's the same. If you are in a lab, you are not going to make a square, impossible to make. You will do a connecting wire to here, a connecting wire to there. So all these are in parallel, these are in parallel, and these one are in parallel. It's the same thing, because they are in parallel. That's why. Okay, so let's try to do this one together. You have, so now if you can see, it goes like this, and then you have 2 branch combine, 2 branch combine, go here. So try to do this one. So this one, the 100 and 300, they are in series, okay? They follow each other. It's like a big zigzag. So it's gonna be 400. And then those two are in parallel. Yes? 10. So it's gonna be 10, very good, 10. And then boom. And then this one, which is green, is also in parallel. So you have to do 40 to the minus 1, enter, plus 10 to the minus 1, enter, 8. You sure? Yes. Okay, so I don't need to show you, it's good. Okay, 8. 8 ohms. Yes? You agree? And all those components, this one, and then this component is like a necklace, right? You have one bead, and then one bead here, and then one bead there. So they are all in series, right? So you're gonna have 400. No, that's 10. It's pink. 10. 40. What is it? 400 and 8. So it's gonna be what? 4. 428. Yeah. 428. Yes. Oh. Any question? Yeah.
Why is the 6 on the side? That's the additional last. Oh, okay, I didn't see that.
Oh, yeah, I'm mixed up. It should be the yellow one should be here, right? Is that clear?
Yeah, thank you.
Okay, so let's try. Why don't we try to do this one? What do we want? Okay, so try to find you see the difference between two. Try to find the current here, the current there, the current there, the voltage drop across here, across there. And I don't know how to, don't know which way. You could do it in your head if you want. So you to find the equivalent resistance, you can do it in your head. Or otherwise, it's we can do it this way. So this one is in parallel, so that's going to be 30 followed by 30, so it's going to be 60. Okay, so I'm going to make my drawing. Okay, so go from here, ta ta ta. You have two branch, so two pipe. One is 60, one is 60, and then they combine together, and you have 30 here. So this one, it's going to be 30. Okay, because they are in parallel. This one is 30. So then I have a big zigzag, boom, 60. So what's going to be the current? 2 amps, very good. And then you take one step back. So this is still 2 amps here because they are in series. So that's one big pipe. Now, what's going to be the voltage drop here? So drop. So imagine it's a pipe. So you are falling down. So it's going to be the voltage drop is Ohm's law.
Oh, I put in each third.
60, right? And this one is going to be 60. So one more step back. So this is 60 volts, and that's going to be 60 volts, okay? Because it's the same height. This is high, this is the base. So where is my current? I forgot to draw the current here. This is 2 amps. 2 amps was here. So this is 2 amps here. Has to be 2 amps coming back to base. And because they have the same size, so here we're going to have 2. And then how much in each pipe? 1. Okay? So if I want to find, for example, what is the energy consumed every second by this load? Okay, I can use 60, so the voltage, 60 times the amp. So that's going to be 60 watts. Okay, or I can use V squared over R, or I can use R times I squared, and you still get 60 watts.
Sorry, Professor. Actually, I'm
60 watts. 60 watt by this one. How much is by the other one? How much power consumed by this one? So same, right? So you have this one is 60 watts. This one is what? So it's 60 watts. This one has an appetite for 60 watts. How much is this one? What's the power? What's the energy consumed per second? How much current is going through? 2. So V times I, that's going to be 120 watt. Okay, so the energy consumed by the load is going to be 60 plus 60 plus 120. How much is that? 240 watt. And how much is energy? Energy is produced by the power supply. It's going to be, what's the voltage? 120 times, what is the current going through the power supply is 2. So that's going to be, okay, 240. So whatever comes in has to come out, something like this. Right. So you remember when we talk about current, the current is going through it, through the power supply. Okay, any question?
And then would you just add up their total powers for each thing to get like the entire total power of the entire?
Yeah, that's what I did, right? I did this one, which is 120, plus this one is 60, plus this one is 60. So that will be 240 watt. That will be the energy consumed per unit second. And that will be the energy produced by the power supply. So when you are looking for charger for your laptop, you look at the power. Okay, so sometimes there is 3 things: power, voltage, current. So if you are given the power and you are given the current and not the voltage, you can find it. So that way you can buy a cheap power supply like I did here, even though my computer is complaining, you see nothing happen. They don't want me to buy something cheap. That's it. But you have the same amount of power, the same voltage, and the same current. You're not going to fry it, right? Okay. So I don't know if I had like here 120 60. So we just did this one. No. Okay, that's fine. Okay. What about this one? So a different way to do it. You see how you have one bead here and then you have another bead here and they're all connected to the 45. So you have 3 branch. Now you can do that if you want. Tung tung tung, tung tung tung, tung tung tung, and boom boom boom. 10, 15, 15, 15. So let's take care of this. What's going to be the equivalent resistance here?
15.
So 15, 15, 15 parallel. So it's going to be 5. Okay, 15 divided by 3. Otherwise, you do 15 to the minus 1 plus 15 to the minus 1 plus 15 to the minus 1 to the minus 1. And you have 10. Okay, and here everything happens like you have a big zigzag. How much is that? Ohms. So what's going to be the current? 3. So here it's going to be 3. So what's going to be the voltage drop here? 15 volt. What's going to be the voltage drop here? 30. Very good. So that's going to be 30. That's going to be 15. And here you are training 3 amps. And here it's back to the 3 amps. Okay? So here it's easy. You have 15 divided by 15 is 1. Okay? You see how it works? So if I go back to my slide here, okay, so let's measure the current. Current is 3, 3, 3, 3, 3, 3, 3, 3, and then it's going to split in 3 because it's the same load. You see, current is 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Come back, merging together again is 3, 3, 3, 3, 3, 3, 3, 3. Even 4, all the power supply is going to be 3. Okay? Now, if you measure the voltage drop here, measuring the voltage drop, you're going to get 30 volt, right? So 10 times 3 is 30. The whole voltage drop is 45, but the voltage drop across the branches is 15 volts. Okay, is that clear? Okay, so you see, when you have a circuit in parallel, all the branches have the same voltage drop. You see here it's going to be 15, and here it's going to be 15, and here it's going to be 15. Any question? And if I replace everything, what did we say? What's the equivalent resistance? 1? 15. So here I go 15. You see 3 amps. 3 amps, 3 amps, 3 amps, 3 amps. Everywhere you have 3 amps. Is that clear? And the voltage drop is 45. Okay? It's important because even if you work in lab, you always have those electrical stuff, electronics. So okay, let's do this one in our head. So first of all, we take care of this one. 300. In parallel with 300, that's going to be 150. In series with 400, it's going to be 550. Okay? Remember those equations here for the power consumed. You have 3 equations. P equals VI or RI squared or V squared over R. So this one, which one you want to use? V squared over R, very good. Okay, so you see power is 60 watt and the voltage drop is 85 volt. So power equals V squared over R. That will be the equation to use because otherwise you're going to lose, you're going to mess up if you go step by step. So it's easier to use that equation. So it's going to be 60 divided by 85 square over R. Right? So you cross multiply, divide.
That's people working.
1. Just to do my proportion right.
120.4.
Wow.
I'm always right, except when I'm wrong. When I'm wrong, you go back to the first.
General silence. Français. Parler français.
Parler français.
Let me practice again.
Okay, so is that going to work? So remember when I show you how to make a lemon battery, and I told you that you have a copper, zinc. Copper is plus, zinc is minus, and you only provide 1 volt about. So if you want to increase the volt, you put your batteries in series. But you want to make sure that minus goes with plus, because otherwise they're going to kill each other out. So let's look at that circuit. So first of all, when you have a circuit, it's like commutative. So it means like 2 plus 3 is the same thing as 3 plus 2. So the order doesn't matter. So it doesn't matter if you place the battery here or close to this one. Okay? So you have 2 batteries. Is there something wrong here? Very good. Minus and minus face each other. So what do you think is going to happen? They're going to kill each other out. But this one is 24, this one is 6. So everything happens like you have a power supply of 18, right? 24 minus 6. So everything happens. So you can make a schematic with a power supply of 18 volts. And even though they are not touching each other, they are still in series because it's one thread. Okay? So 12 plus 8 is 20. So 20 ohms and a power supply of 18. That's so everything happens like you have a circuit with 20 volt, 18 volt and 20 ohms. Okay? So everything happens like you have 24 minus 6 and resistance of 20 ohms. So that will be 18 divided by 20, which is 0.9 amps. Is that clear? This kind of makes sense. There's nothing special about that. Okay, so circuit in parallel. I think I have like I just found like a simulation. I am into simulation now. That's what you're gonna see for your pop quiz. Okay, I just want to go over one problem from your textbook, I think, not textbook assignment. So anyway, these are the equations so far. That's all you need about for your test, right? So you have all the equations there. You see energy consumed will be power times the time. Do remember how to find the price, like if you consume that much kilowatt hour. So then if you know that it's 25 cents per kilowatt hour, so you know the price. So let me take one more example from your homework. Okay. Like if you have something like this, well, I don't know, I have to go back to the homework, but if you have something like this, you have like 10 ohms here, okay, and then you have a branch, 20, and then you have 20. I'm thinking. And then you have 10. Let's make it a little bit more challenging here. And then you have another one here, which is 30. Okay. So first of all, you can already find the equivalent resistance. I'm going to make 30 here, okay? So it's easier. So 20, 10, 30. And I'm going to take a power supply of 110 volts. And let's say I want to find how much the ultimate question, I want to find the power consumed by this one, say. Only by this one. So what's the equivalent resistance did you find? 55. Do you all agree with that? Okay, so you take that 10 here, and then 2 and 10 is 20 and 10 is 30. 30 and 30 is 15, so it's 10, 15, and 30, right? So now let's find so I have 10 here. So that 10 could be next to the 40, okay? We don't care. So here we say 30 because they are attached to each other. And then you have 30 here. And then you have another 10. No, another 30. Is that right? No, this 30 could be placed here. Doesn't matter, okay? Because you have like 3 components. You have this component here, and then you have this component there, and there are this component. So you can change the order of the components. So then you have this one, so 110, and then this one is 10, and this one is 15, and this one is 30. Okay, so everything happens. I have one big boom, 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 and that will be 55 ohms. Do you agree? So what's going to be the current? 2 amps. Do you agree? Okay, so that means here it's going to be 2 amps. It's like a pipe. Do you agree? So let's find the voltage drop. What's going to be the voltage drop here? 20 volt. What's going to be the voltage drop here? It's going to be 30 volt. What's going to be the voltage drop here? 60 volt. Yes? Okay, so that's here, it's going to be 60. That here, it's going to be 30. And that here, it's going to be 20. Do we have the right account? 60 plus 30 plus 20, is it 110?
Yes.
Okay, so it's good because otherwise it will be not good. So this one is 2 amps, right? This one is 2 amps. So how much in each branch here? 1. Do you agree? Okay, so that means here you have all that is 2. And then that's 1 amp here. That's going to be 1 amp, right? And that's going to be 2 amps. And coming back to 2 amps. Yes? So let's think. Okay, I want to find the power consumed by this one. I do not have the voltage drop, although I could find it. Do I have the resistance? Yes, what is the resistance?
20 ohms.
20, very good, 20 ohms. Do we have the current going through that 20 ohms? What? Okay, do we have an equation? Very good, R I square. So P equals 20 times 1, which is 20 watts. Okay, so the voltage drop here is 30. So if I want to put my voltmeter, okay, if I want to put my voltmeter, you see, it's gonna be 30 volts here. And across this one, it's 60. And across this one is 20. So we have a 60 and 30 and 20. Is that clear? That's it. Okay. So if I want to find the voltage drop here, it's going to be V equals RI, right? So it's going to be 20 volt. Yes? And around here, it's going to be 10 volt. Do you understand how it works? So I highly recommend. So these sims here are amazing. All you have to type is FET sim DC circuit, and you can really build the circuits.
Sure.
Which one? This one?
How did you get one?
This one?
With the
Well, where do you see 1 amp? Here, because it goes back to here. So you have 2 amps, and this one they have the same resistance. No, or you can do. You see, 30 volt is the voltage drop. So 30 divided by 30 is 1. The voltage drop here is the same because it's in parallel. So 30 divided 30 is 1. And they have the same resistance, so the same size. Okay, so it's going to be the same current. And then they combine together. Is that clear? And then it can become a headache, those circuits, but I think we're not making more complicated than that. It's important because actually there was a Nobel Prize, I forgot, in the 70s, something like this, that shows that you can understand how neurons work by with an electric circuit, by using a small electric circuit as a model. Okay, any question? So, what else? So, safety, okay? You see, sometimes you have machine with only 2 prong. That is not the norm anymore, but I have seen those. Not machine, but I've seen old machine with 2 prong. So if you see 2 prong, that means you are missing the safety here that connect to ground. So remember here you have the ground, which is safe. Okay, remember I plug something inside, I was fine. And then the small one is the hot wire that will provide 120 volt relative to the ground. And then here you have the return path, which is also supposed to be connected to the ground, but it's not that safe to touch it. Okay, so don't put anything inside. So what's happening here, because you are missing the connection to ground, okay, if there is like a wire that is cut inside, it can happen, those mice or rats or whatever, they can chew on wires, so that can happen. And because you don't have the connection to ground here, you will be return path, okay? Because remember, in a house, okay, the return path is through the ground. So that's bad. So always wear good shoes, not flip-flop, even if you are doing your laundry, because you never know. Okay, a little bit about AC voltage. So I told you that the electricity we get from the outlet is AC, so alternating current. So the voltage, it's what it does. So let me show you. I have an app here. So the hot wire is going to increase up to the peak voltage is going to be 170, but when you measure, you get 120. I will explain why. But anyway, it's going to increase and then it's going to decrease and then it's going to increase. So if you look just at the hot wire is going to be minus, plus, minus, plus, minus, plus. So what it does is that when you have AC, you see the current is flowing in one direction, the other direction, one direction, the other direction. That's called alternating current. And why? Because otherwise you cannot transport electricity over those high tension line. If it's not alternative, if it's DC, you cannot do it. You can do it only if it's alternative. Okay, so this is called AC. And you see that if you are looking at the current as a function of time, it's constantly changing direction, go back and forth. So it has a frequency. So I'm going to define what frequency is. What is that function? It's a sine function. Okay, it's a sine function. So that will be for the current. Now the voltage, it's going to be the same. I'm going to also get a sine function. See, it goes up to 10. So 10 will be the peak voltage, goes up and down and up and down.
Cosine?
It will be a sine also. Or cosine. Actually, it doesn't matter because sine and cosine, they are just off by a shift by 90 degrees. So anyway, the most important thing to understand is it's going to be a sine wave. Why do we make it a sine wave? Because sine waves, oh, I'm getting tired. Sine waves are very cooperative. You can add them, it's going to be a sine wave. You can multiply them, it's going to be a sine wave. You can multiply by a constant, it's going to be a sine wave. Okay, so when you are doing electronics, it's easier to deal with sine wave. So it's on purpose that they are looking like this. Okay, so then we're gonna it will be very much like when you have a simple harmonic motion. So I'm sure I already show you that from last semester, but let's see if I have. Okay, you see, that's called a simple harmonic motion. See that? And that's how the current is going to behave. Okay, it's going to go in one direction, the other direction. Now the distance here, the time it takes for one cycle, it's called the period. Okay, and the number of cycles per second, it's called the frequency. So I'm going to show you that. Where is my example here? So what is the frequency here? 0.5 hertz. So this is 1 second. So this is one cycle, okay? So the current goes positive, increases, go to 0, negative, and goes back here. So that will be one cycle. And this is 1 second. So what's the time for one cycle? 2 seconds. Do you all agree with that? You see the current goes up and then 0, and then it's negative, and then goes back. So one cycle is, in that case, example is 2 seconds. Okay, so the time for one cycle in physics is what we call the period. And the unit is in second. Notation is T. Okay, so let me define it. So T, okay, it's called the period, and it's the time per cycle. Okay, so it's in second. So in that case, the cycle is 2 seconds. Do you agree? Okay. How do we find frequency? the frequency is how many cycles in 1 second. So you see, in 2 seconds, I have 1 cycle. So in 1 second, how many cycles do I have? Half. Very good. So that will be the definition of the frequency. So the frequency is just the reciprocal. So the frequency is the number of cycle per second. And the period, I should write like this. The period is the number of seconds per cycle. So 1 cycle here is 2 seconds. And the number of cycles per second is called the frequency. Okay? But we like to confuse students. So instead of saying cycles per second, which is 1/second, the unit is hertz. Okay, it's named after Henry Hertz. Okay, so frequency is the number of cycles per second. The unit is hertz. So for example, here, what's the frequency? 0.5 hertz. So in 1 second, it's gonna go like half. So example, if I do this like 1, 2, 3, 100 times, so I go up and down, up and down, up and down 100 times in 1 second, the frequency will be 100 hertz. Okay, so if I go up and down, up and down, up and down 100 times in 1 second, the frequency is 100 hertz. Is that clear? What's going to be the period? It will be 1 divided by 100. Is that clear? Okay, so that will be the definition of frequency. And here the peak is 10. So how do we connect that to the outlet here? So in our outlet here, okay, so you have like this is here, that's the ground, we don't care. And here you have the return path that's supposed to be also connected to the ground at some point. And here you have the hot. This is the hot wire. So the hot wire will be plus, minus, and then it will be minus, plus, and then it will be plus, minus, right? So that will go 1 cycle. The frequency from the outlet, the frequency is 60 hertz. So how many times does it change sign in 1 second? 60. So you have 60 cycles for 1 second. Okay? So what does it mean? It means in 1 second it's going to go up, 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 in 1, and then 2, and then 3, and then 4, and then 5, and then 6, and then 7, and then 60 cycles in 1 second. So that will be the definition of the frequency. So the frequency here is 60 hertz. Of course, we cannot do anything like others are doing. If you go to Europe, it's not going to be 60 hertz, it's 50 hertz. Okay, so why? Don't ask me why it's 60 and Europe it's 50. But in both cases, it's alternating current. Can you tell me the time for 1 cycle now? 0.01666666 repeating. So 0.02 seconds about. Okay? So that will be the period of the signal. Yes.
So what's actually causing it to shift signs? Is there like a
Oh, very good question. Excellent question. So it takes you back. How do we produce electricity in the first place? Okay, so how do we produce electricity? Here again, you have Okay, so electricity is produced here, and then we make it to a high voltage. Okay, so smaller current, so we don't lose too much heat. Da 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 da. And then you have like looks like a cylinder that you can see. It's going to bring back the voltage to 40 volt. But how do we produce it inside? Inside the power plant, um, that will be the principle. So it's called Faraday's law of induction. So here it's the way it works. This is your house here. This is your power plant. And you have a wire, so it's a coil going around and around and around. And you take a magnet. So of course it's not going to be a magnet, it's an electromagnet that will be pushed in, pushed out, pushed in, pushed out. So that's where the frequency comes from. So it's being pushed in, pushed out. How many times per second? 60. Okay? 60 times. So in 1 second, you go in, out, in, out, in, out, in, out, 60 times. So that will be the frequency. That's where you get to your house. Here, you see here the hot plug, the hot connection here. The small one, it's going to be what? 120, 0, minus 120, 0, 120, 0, minus 120, 0, and so forth and so on. It doesn't matter, okay, for our electronics, because now we have those charger. Okay, so my laptop does not like alternating current, yours neither. So that's why you have those box here that will turn alternating back to direct DC. But why do we have to do that? Because otherwise you cannot transport electricity over a very long distance. So in the power plant, you need some, of course, you need some energy. So how do we get the energy? Power plant. We use it, you use, for example, steam. So steam that can make a turbine spin, right? So you have to use some fossil fuel. You can use coal, you can use natural gas, you can use nukes, for example. So all that are very efficient. So 60 times in and out, that will be the frequency, 60 hertz. So if I ask you for the test, what's going to be the frequency of the outlet, you're going to say 60 hertz. And the period will be about 0.02 seconds, 0.016666666666. So that will be how long it takes to go from here, there, and back there. So that will be the period. Or how long it takes to go from here, back to here, and back to there. That's what we call AC. Okay? Now, look, why do we want to use sine wave? Because they are so easy to, for example, if you want to plot. Okay, so let me show you plot Wolfram Alpha. It's an amazing tool. By the way, if you have a math class, you can have a student account and they will break you everything down. They will break down all the problems. So if I do plot, so I want to have a voltage with a peak of 10. So I'm going to put 10 here. So you always have you 10 times sine. Okay. You always have a 2 pi. So I'm going to put a 2 pi x divided by, what do you want for the period?
Thank you.
A period of 2. Okay. That sounds good. And for x between 0 and 6, for example. How beautiful is that? Do you see how easy it is to make a sine wave? Here, you always have the peak here. There is always a 2 pi, There is always an x, because x could be the time. And then the period is always at the denominator. So that will be the time for one cycle. Get that? Okay, so let's take let's talk about this one. This one, the peak is not 120. So when you are measuring, and we'll explain, but when you are measuring, like last time I did that, I measure 120. But 120 is like an average value. The peak is 170. So I'm going to put 170 here. I'm going to put 170. And here, what's the period? We say 0.02, something like this. I'm going to make it smaller, 0.2. Okay, so you see the peak here is 170, and the period, you go up, you go down, go back to the same place, that's going to be 0.02. You see how it works? So each time you have a periodic function, so a sine wave. Matthew, you are not sleeping, right? No? So always have the peak here and the period here at the denominator. Is that clear? The only confusing thing, okay, that's the only thing that is confusing, is that for the outlet, okay, electricity from here, we are not measuring the peak voltage. So this is the peak voltage, which is about 170 volts. So I'm talking about this outlet. So if I was able to measure with an oscilloscope, okay, I will see the peak voltage is 170. But when you are measuring with a voltmeter, we are measuring like an average, which is called the RMS average. So the root means square, and that's going to be 120 volt. Why? Because only if I use the RMS can I use Ohm's law. So I don't want to explain all the details, but it's not that hard to remember. So you have the hot here, the return path, the ground. When you are measuring, you're going to measure 120 volt. So you ask me, how do you go from 170 to 120? Right? And you take 70%. That's the equation. So you take square root of 2 times 170. What do you get? Square root of 2 times 170. No, 240. So that's going to be 240 volt, not 120. But that's how 240 will be if you have a big machine, 120 and 120. So if you have 120 volts, what's going to be the peak value then? 120 volt times, no. What I'm talking about. No. Sorry. Yes, it's 70%. Do 70%. That will be easier. Don't forget about the square root of 2. Actually, you divide by square root of 2, but forget about that. Just do 70% of 170. What do you get?
119.
Okay, 120 volt. Okay. About 120 volts. So that's a secret. When you have a voltmeter, you're going to measure 70% of the peak voltage. Okay, so that's why when you make a circuit, you have to be very careful, because the maximum here is not 120, it's going to be 170. So conclusion, voltmeter, when you are measuring a voltmeter, you are measuring 70% of the peak voltage. Okay? Are you with me? Okay. Just about wave, we'll see that on Thursday. Okay, we'll see that on Thursday. We're almost done, but you see the hot wire keep changing. All that is written there. See, in Europe, the frequency is 50 hertz. And in Europe, the voltage, the RMS is 220 volt. Here is 120 volt. Remember we discussed that. Okay, so now I think